Hello, and welcome to today's daily Leetcode challenge. Today we'll be solving question 1361, validate binary tree nodes. So it's the medium level problem. I'll be going through my thought process as I come up with a solution, then stick around for the end of the video where I compare my solution to the solution of others. With that, let's begin the question. So here you have n binary tree nodes numbered from 0 to n minus 1. Where I has two children. Let me just get this. I has two children. Left child and right child. Return true if and only if the given nodes form exactly one valid binary tree. So what is a valid binary tree? A valid binary tree is where it is a connected graph, a one-way directed graph with no cycles, where each node has at most two children. That automatically means that there is at least one node that is the root node, which we see here. And as you can see, the properties hold for the rest of the nodes too. They are all connected one way, not bidirectionally. There are no cycles, and they all have at most two connections. So return true if and only if all the given nodes form exactly one valid binary tree. If node I has no left child, the left child will equal to -1. Similarly, for the right child, note that the nodes have no values, and Note that the nodes have no values, and that we only use node numbers in the problem. Nodes have no values. Okay, so that's just clarifying that the nodes aren't represented as actual class structure and that they don't have any value. The index of the left child and the right child arrays actually signify what is visualized here. So what is the process of figuring out, or even figuring out what these two properties are? These properties that, let's say, one, no cycles, and two, let's say that at most two child nodes, and three, I guess, all connected, right? Because there is a situation where you can have disjoint trees, but that's not what we want. We want one binary tree. Okay, and then let's look at the examples quickly. We have 0, 1, 2, 3. This is valid. And the way that they build it is the 0th index of left child and right child point to 1 and 2 respectively. If we were to look at the 1 place, we see that it's both -1 and -1. That means that it has no children. For 2, it has a left child, but it doesn't have a right child. And 3 has no children, so both -1. Okay, output true. What about example 2? Example 2 is false because okay, so another property. It's not that it has at most two. It's not only that it has at most two children. Let's write down another property that we want to take care of. Has at most one parent, right? Because all of these properties check out for this example, but 3 has 2 parents, which can't happen. Okay, and this is false, obviously, and there's no explanation, but it's pretty self-explanatory. And okay, and what about in this case? What problem doesn't? Well, this is a cycle actually, right? Because this is a cycle. You go from 0 to 1, then 1 to 0, then 0 to 1, and so on. It's a cycle. So far I've collected 4 properties that I need to take care of, and they are here. So the no cycles we can use simply like a visited array. And once we're traversing, since we're traversing the the tree, if we encounter a node more than once, then that means that there is a cycle. At most 2 child nodes. This one is actually, now that I'm thinking about it, is completely not needed because we're already guaranteed to have at most 2 because we're only given a left and a right. We're only given a left and a right array. So that brings us just to 3 properties that we need to maintain, all connected. This actually also could probably be done with a visited array. Why I say that is because by the end of the traversal, if we see that some nodes have not been visited, we can automatically say that the tree is not connected. And at most one parent. So having more than one parent means that you would actually visit it more than once. So, I mean, visited. All right. It should be clear that at this point, it's the visited array is simply what we're going to be using for this case. Now how do we traverse it? Traversing it, I would do like BFS, I guess, is probably the easiest because BFS doesn't require any sort of recursion. By the way, BFS just requires a queue that you're going to be dequeuing from the right and appending to dequeuing from the left and appending to the right. The idea is you would start with the top node here, and then you would look at the left and the right, and then you would look at the left and the right nodes, and then you would add them also to, you would have the 0 here, 1, 2, then you would look at the left and the right, you would pop this element, you would append this here and append this here, and then until the dequeue is non-empty, you continue adding it over and over again for the left and the rights. So that's there. That's going to be our traversal algorithm. Now, I think we're ready to actually start. Let's. Should I explain a bit more how breadth first search works? Yeah, let me elaborate a little bit. BFS, breadth first search, means that you are in this drawing here. You're looking at level by level. So you're iterating over the tree layer by layer. You initially start with a queue with the 0th element. You pop that element from the array, and you look at what children does that. You pop the element from the queue. You look at what children does this have. This would have 2 children. These are 1 and 2. On the second iteration, I would pop 1 and check what elements, what children it has. It has none, so I'm just going to be left with a 2. And 2 then has 3 as my child here. So I would just have 3, and that way I would in 3 sort of by looking at 3 nodes, I would have looked through all of them, the whole tree. Okay, so let's start. So I want the queue, dequeue. I'm gonna start with the 0th node, and I'm going to say that while q node equals q pop left, as I said before, and now I'm going to have the visited array, right? Visited is equal to false times n. N is the number of elements in the array. So now I would say that if visited, if the node has already been visited, definitely return false. This means that I've encountered this node before. If not, visited of node is equal to true, meaning that I've now visited this node. Now, if, let's call this left, left is going to be left child of node, and if left child does not equal -1, then I'm going to say q append and this value right here. Same goes for the right. If right child node does not equal -1, q append right child node. Cool. So now that I've traversed my tree and made sure that I'm not running into these situations, no cycles with a visited array, meaning that I've only assigned true to a value once, all connected, not yet done, and at most one parent. So far I've taken care of 1 and 3. What is left? Well, what is left is to make sure that all the nodes that are passed to me are connected. And the way that I would do that is make sure that all of these values in the visited array are eventually true. So I could just return all visited. Now this would just make sure that everything is visited. That all the values in the array are true. So that seems to have worked. Wrong answer. Interesting. What is this example? I've taken care of all of these. Let me see. I'm starting with 0 as the root node. Okay, so 0 has a left child of 3, a right child of none. Left child of 3 is none, so this should be a disconnected, unless 0 is not the root node. And nowhere here does it say that 0 node has to be the root node. So there is a chance that actually in this case it seems like 2 is the root node, and then 2 has a left child of 1, which has no left or right, and a right child of 0. Right child has a left of node 3, and that's it. Okay, so actually, I mean, let me draw this out. This is what the tree looks like. And the problem here is that we're starting at 0, right? So we're just looking at 3. We're not looking at 2 ever, because the way that we traverse it is by looking at children, not at parents. So we don't have a backward way of looking at it. So actually, all we need to do, it seems like, is to find the root node. I'm gonna make this into an array. I'm gonna make a set of left and right children, and just find the number that does not appear from 0 to n. I'm gonna find a number that doesn't appear there. So what is this? Children is equal to set of left child union set of right child. That just gives me a set. Now for I in n, in range n, I'm going to say if I not in children, I need this to be over here, root node append I. And let's say if we happen to find more than one root node, then that's an issue because we should only have one. False. And now that we have this here, let's return the 0. Okay, let's use this test case. Now in this portion here, I'm just making sure that I only have one root node, but it should be good. Cool, and we're beating. Wow, we're on the top, which is awesome. I wonder what some of these other solutions are. They might just be. Might just not be a popular question, guys. I think we did very well. This is very thorough. BFS is fast and makes sure that we only visit each node at most once. If we don't visit it, if we visit it more than once, then we automatically leave the traversal and return false. This is very fast and intuitive, so definitely use this. Especially that it beats mostly everyone. Cool. With that, thank you for watching. Now check out the other videos that I do in Rust. Rust is extremely fast, low-level language that has a very hard syntax. So I'm trying to learn that and share that with you guys also. So, all right, thanks for watching. See you later. Please like and subscribe. Bye.